Welcome everyone, and this is the final seminar for this semester's data science seminar for the Electrical and Computer Engineering department here at Rice. Welcome, and it is a great honor for us to have Professor Cynthia Rudin with us this afternoon. Professor Rudin is a professor in computer science, electrical and computer engineering, and statistical science, mathematics, and biostatistics and bioinformatics at Duke. She directs the Interpretable Machine Learning Lab, and she mainly works on the design of predictive models with reasoning processes that are understandable to humans. So her areas of research are machine learning applied to healthcare, criminal justice, energy reliability. She holds an undergraduate degree from University of Buffalo and a PhD degree from Princeton University. Professor Rudin has won many awards. Importantly, recently she got the Squirrel AI Award for Artificial Intelligence for the benefit of humanity. This is one of the most important award inside AI, not only for technical advances, but because of the implications of the results for the benefit of humanity. This is sometimes considered as the Nobel Prize of Artificial Intelligence. But that's not the only prize she has gotten. She has many other prizes, including the Best OM Paper in Operations Research Award from Inference, the Fico Recognition Award for Explainable Machine Learning, and some other Inference prizes on innovative applications for analytics. So again, it is a great pleasure to have you here with us this afternoon. Fortunately, it cannot be in person, but I guess everybody is looking forward to listening to your talk. So welcome, and you can start sharing your screen. Thank you.
Great, thank you. Okay, so you should be able to see it now. So I'm going to talk about scoring systems, which are really tiny little models at the extreme end of interpretable machine learning. It's hard to believe the power of a little itty bitty model. So before I talk about scoring systems, let me ask you a question. Can a typographical error lead to years of extra prison time? Right, that should never happen, right? Typos making decisions, right? That's crazy. Who's making decisions here, a judge or a typo? And is that fair? But it happens all the time. And here's an example. So this is Glenn Rodriguez, who was in prison since he was a kid. And he was denied parole because his COMPASS score was miscalculated. And COMPASS is a proprietary black box model for predicting future crime. And it's used in parole decisions. And yes, a typo made a decision here, not a judge, a typo. And he got years of extra prison time. So just some definitions. A black box model is a formula that's either too complicated for any human to understand, or it's proprietary, which means we're not allowed to understand it. And then on the other extreme is an interpretable machine learning model, which obeys a domain-specific set of constraints so that humans can better understand it. So why do you need interpretable machine learning? You need it when you have high-stakes decisions or troubleshooting. So basically, anytime it would be really bad if the model went wrong. Because a lot of times AI models do go wrong. They can go really, really wrong. Okay, so what else can go wrong? So we already know that we could send people to prison based on typos, but what else happens? So I put up two of my favorite articles where black box AI models went wrong and no one was able to figure out what happened. So the article on the left, this one over here, is from a black box AI model that told everyone that it was safe to go outside during the California wildfires, and that air quality was fine on days when it was not. Like people were seeing a layer of ash on their cars, and yet Google said air quality is fine, everything's fine, and no one knows what happened there. And then this article is about an FDA-approved deep learning model for detecting intracranial hemorrhages that when they launched it out into the world, it didn't work and no one knew why. And this model was FDA approved, which is kind of, crazy if you think about it, right? So these even these FDA-approved models aren't performing as well as they should, and no one knows why. Now, I've given you just a few things that have gone wrong with using black box models, but there's a tremendous amount more that could go wrong, and probably many things have gone wrong that were hidden, so I don't know about them. And now people are starting to use machine learning for medical decision-making, for loan decisions, self-driving cars, and all manner of other things that you really don't want to go wrong. And some people love their black boxes. They argue fiercely about why they need them. Anyway, I want to get back to Compass. Do we really need to have black box models? Are they more accurate? And luckily, there was a data set from Florida that was released several years ago that could tell us exactly how accurate Compass is. Okay, so we took the data from Florida and we tested the Compass scores against a model that we had developed in the lab at the time. We've gone a lot further than Corals, but Corals it's a certifiably optimal rule lists, and it's an optimal decision tree method. It tries to get very tiny little one-sided decision trees or decision lists or rule lists, whatever we want to call them. And in the data set from Florida, we had the Compass scores, but we also had like different characteristics about each person, like their age and their criminal history features and so on. So we fed all that into Corals, and it gave us a machine learning model that was so tiny that it fits in the bottom of a PowerPoint slide. And that model looks like this. It says if the person is 19 to 20 years old and they're male, then predict arrest within 2 years of their Compass score calculation. Else, if their age is 21 or 22 years old and they have 2 to 3 prior offenses, then predict arrest within 2 years of their Compass score calculation. Also, if they have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this model and it was so simple. And we thought, could this really be as accurate as Compass? And it was. So what I'm showing you are 10-fold cross-validation results, and each fold is in a different color. And what you can see is that Compass and Corals are about equally accurate. And we thought, okay, well, that's interesting. I wonder what happens if we just throw the entire arsenal of machine learning algorithms at this problem and see what happens. And interestingly enough, we did not find any better performance from any of them. And some of these models are very large to the point where you couldn't write them on a PowerPoint slide. Like this is boosted decision trees and support vector machines with radial basis function kernels, right? Random forests. These are very, very big, complicated models. And, you know, on the other extreme is Corals, whose whole model is right there in the corner of the slide. So now there was this huge debate about the algorithmic fairness of Compass after the data set was released. But the truth is that we just don't seem to need Compass at all. All right, now you've seen that black box models aren't always more accurate than simple models, but there's some important general knowledge that I need to provide to you, okay? What I showed you was actually part of a general pattern. There's really 2 broad kinds of problems that we encounter in machine learning and data science. There's problems with tabular data and problems with raw data. Tabular data look kind of like the criminal justice data that I just showed you. So this is like a medical example where you have features and then you have either categorical or real valued labels. And then for the raw data, you can have like, it could be like images or sound waves or large bodies of text. And these 2 types of data are fundamentally different, both in terms of the algorithms that we use for them and also the way we define interpretability. Because for instance, like for tabular data, we could want a model that's really sparse, like the Corals model. But for raw data, you really don't want a model that's like sparse in like pixels in an image. That doesn't make any sense, right? 1 pixel in an image doesn't really tell you what's in it. So you have to think about interpretability differently in these 2 domains. Anyway, now for raw data, the only type of technique that's working right now is neural networks. And that doesn't mean that it's always going to be the way it is, but that's how it is right now. Whereas for tabular data, it generally is true that with minor pre-processing of the data, all the methods tend to have similar performance. So in other words, what I showed you with Corals, it's actually with the Florida data, that's actually a phenomenon that sort of works for all, tabular data sets. And what that means is that you can often have these really tiny little models that perform extremely well, depending, on the data set. So while we work on interpretable neural networks, which is obviously a task that a lot of people are thinking about right now, including me, we have to realize that there are tremendous opportunities with tabular data, because we can try to design models that are very, very sparse, that also have the same accuracy as the black boxes. But you have to optimize them really well in order to get up to that accuracy. Okay, so if we think about the history of predictive modeling over the last century, for only a small amount of that time did we actually have data. So most of the predictive models needed to be created by humans. So when we think about what kind of predictive models we want to build now that we have data, and we want these models to be interpretable to humans, we need to think about what types of models humans designed in the absence of data. And the most popular form of predictive model, hands down, was scoring systems. Now, a scoring system is a sparse linear model with integer coefficients. So I'm putting up here a model that is called CHADS2. This is possibly the most widely used predictive model in healthcare, maybe that and like, the APGAR score or something like that. Like this is a very popular scoring system that's used in medicine. But I want to point out that this model is not a machine learning model. This was developed by humans and validated on data afterward. Now, scoring systems have been used for about 100 years, actually, and I'm showing you a slide that is from the Burgess paper on determining success or failure on parole from 1928. And what Burgess says here is that accordingly, 21 factors were selected by which each band was graded in comparison with the average for the 1,000 cases upon the probabilities of making good or failing upon parole. So in other words, what he was doing was trying to create a scoring system for whether someone would succeed or fail when given parole. And so he came up with 21 factors that he wanted to put in his model, and he would add up how many of those factors the person had, and we'd use that number out of 21 to give the person some kind of rating on how likely they were to be successful on parole. So he actually did a lot of this paper is kind of really interesting to read, actually, and it's like 100 years later. It's kind of and cute and kind of scary at the same time. So let me show you some other stuff that he had in that paper. So down here, this is the rating system here, where he's got, if you have 2 to 4 points, you have a 24% chance of non-violating parole. Whereas if you are up in this upper category here with 60 to 21 points, then you have a very high chance of not violating parole. Okay. And then he grouped people into different categories and tried to calculate the violation rate in the different categories. And I thought the categories were really interesting. Like you have like ne'er-do-wells and mean citizens and recent immigrants. Oh my gosh, and farm boys and drug addicts. So it's actually kind of, we don't do this anymore, but we do things that are actually incredibly similar to it, in the sense that we still develop scoring systems. So here's a more recent version of this kind of scoring system. This is the Pennsylvania Commission on Sentencing's score from 2013. And again, it's a scoring system, and you add up the points, and the points translate into the risk of being arrested. They're still the same kinds of models from 100 years ago. And why is that? It's because they're easy to use and easy to understand. This is the Violence Risk Appraisal Guide from 2006. And here I'm going to zoom in, and you can see that depending on the points that you get, and the sum of these points, it can translate into low, medium, or high risk. And then if there's so many of these kinds of scoring systems in medicine that they have web pages that index them by specialty. Okay, there's so many of them. So for example, if you scroll down to neurology, and then you click on seizure, you will get to the seizure scores, and then you click on the 2 helps 2B score, say, and then it's actually a calculator, and you punch information into the calculator, which is actually just a scoring system, and you get points that translates into a risk of seizure in the next 6 hours. The problem with these scoring systems is that when you design them by hand or with heuristics, they aren't very accurate. So of course the question I'll be asking is how to design these scoring systems to have optimal predictive performance according to data, but also be understandable and easy to use by humans. Now, the thing about the 2 helps 2B score that makes it different than all of the other medical calculators is that it was not designed by humans or using heuristics. Okay, so I want to talk about this application for a while because it's actually really important. Okay, so let's say that you have an aneurysm in your brain, which is here, and it bursts. So now you have blood in your brain. It's like a blood explosion in your brain. And you are in trouble. Okay, so you get to the hospital, they give you surgery, they put you in the intensive care unit, and they put continuous EEG monitors all over your head. So what are those monitors checking for? And the answer is they're checking for the possibility of seizures. Now, these seizures are common to critically ill patients. About 20% of critically ill patients get them. Seizures cause brain damage and they cause death. And doctors will do a lot to make sure you don't get a seizure. So they'll even use medicine to shut down part of your brain, for instance, to try to make sure you don't get one of these damaging seizures. Like the seizures can actually be more damaging than the actual injury that you've got in the first place. Okay, so the only way to detect these seizures is through EEG monitoring. These are not seizures where the patient's shaking. This is only happening in the patient's brain, okay? Now, the only way we can detect the seizures is through EEG, but the problem is there's not always enough EEG monitors or staff to go around. And what happens is that the monitors stay on patients way too long, and then patients who need them don't get them. So we need to figure out how to allocate our EEG monitors so that we can predict seizures accurately and help allocate these monitors, properly to reduce brain damage and save lives. All right, so we worked with neurologists to develop the 2 helps 2B score, which is the one I showed you on Medscape. And it's now widely used in hospitals, and it's small enough that it can fit on a PowerPoint slide, but it's also as powerful as our best black box learning models. And if you enter the information in the screenshot we saw earlier, it'll compute the 2 helps 2B score. So 2 helps 2B is called that because it's 2HELPS and 2 points to the B, so that the doctors can memorize the whole model just by knowing its name. And then you get points for different signals in the EEG, and then the total score translates into a risk using this table down here. Now, I know it looks like a rule of thumb, but it's actually a full-blown machine learning model. It was not created by doctors. It was created by data fed into a machine learning algorithm. Like I said, it's just as accurate as black box models. Doctors can decide themselves whether to trust it. It's not like a black box where it forces you to trust it. So here, doctors can decide themselves whether they want to trust it. And they don't have to trust it. They could say, and can just choose not to use it. They can also calibrate the score with information not in the database. So for instance, if the patient has something special about them that's not in the database, the doctor can say, that patient, they need an extra point because they have this special characteristic about them. And also the score could be explained to non-physicians. So you can explain to someone why their relative is being taken off of CT monitoring, for instance. Now, you might say, well, there's only 6 factors here. This isn't hard to construct this, but the truth is that these 6 factors and the points and these risks were all chosen from a much bigger data set. So the data set had over 70 factors, and the algorithm chose those 6 and figured out what the points should be and what the risks should be. Now, since the model is simple, you might think that it's easy to construct these kinds of scoring systems, but it's not. There's actually a combinatorial explosion in the number of model options to choose from, right? First of all, okay, let's think about what the constraints are, right? So the challenges are that you really want the model to be as accurate as the best black box. You want it to have only a few terms, perhaps some custom constraints like fairness, and you want it to have integer coefficients, like 1, 2, and 3 and not 27 or something, right? We want the same thing as what people have been doing since 1928. Now, the typical approaches that people use to create scoring systems are, well, first of all, you could just ignore the data set and then have a panel of humans construct the score, which is a very popular thing to do, as I mentioned. But maybe we can do better if we look at a data set. Then the most common approach is some kind of ad hoc fiddling with logistic regression, essentially. So basically, it's like ad hoc feature selection, then you do logistic regression on the features, then you scale the coefficients, and then you round the coefficients, and you just fiddle around with it until you get what you want. The problem is that these methods don't work. They produce suboptimal scores, and they rely on humans to do high-dimensional constrained optimization. So let me show you an example of where this goes wrong. So this is an elastic net model for the seizure prediction problem for just a few variables, but it's difficult to use, right? Because if the patient has prior seizure and like patterns superimposed with fast or sharp activity, then like how far is their score from 0, right? Or what would need to happen to get their score to 1.6? Can you memorize this model and use it on a patient as you're dealing with a million other things? Probably not, right? Especially if it has more variables in it. Okay, so we don't like this model. Let's try rounding the coefficients. All right, that didn't work. I lost almost all the signal and my probabilities are a mess. Okay, so let's try again. This time I'm going to take all the coefficients and scale them by multiplying by a constant, best factor I can, and then I'm going to round, okay? So I did that, but it is better, but it's again not very accurate, and it's really not what I'm looking for. It could be that if I keep fiddling with it, like I could get something that looks as good as the 2 helps 2b score, but it would be hard to get something as nice as the 2 helps 2b score. And fiddling is just not what we should be doing in this case. We should be actually formulating and solving an optimization problem to get the answer. So if computation was not an issue, okay, what optimization problem would we solve? And I claim it's this one. Okay, so this optimization problem has 3 important pieces. The first one is the logistic loss, which is used in logistic regression, okay, and that keeps things accurate and risk calibrated. Then we have this term over here, which keeps the model nice and small and has only a few non-zero terms. And then this set of constraints over here forces your model to have small integer coefficients. So it could have coefficients between -10 and 10 if you wanted it like that. This is actually the formulation we used to develop the 2 helps 2b score, and it chose 1s and 2s, not choose -10 anytime. In any case, you can also add optional constraints in here too, like if you wanted some fairness constraints or something like that. Okay, so let's say this is the problem we want to solve. And so you could see geometrically like why this problem is so hard now. Okay, so let's say that we just take the logistic loss and integer coefficients. Let's forget about this term. Okay, so we just have these 2 constraints, what's going to happen is that that alone is a mixed integer nonlinear program. It's really hard. But let's see geometrically what happens here. So this is the logistic regression solution, and these are the level sets of the logistic loss, okay? And then if you try to round the coefficients, what would happen? Well, you'd end up at these points, one of those points. But the problem is that here you had to go against the performance gradient. Like you lost accuracy substantially when you did that. And instead, you actually optimize, you would find out that there is a solution with very low logistic loss that's right on, a set of integer coefficients that you wouldn't have known about if you had just rounded, okay? And you could say to me like, okay, well, I think these long skinny areas of low logistic loss, I think that's unrealistic. But they're not, okay? Most problems are like this. And if you if you, this is like the whole reason for the field of mathematical programming, right? Because you can't just round everything to get a good solution. And also, if you have additional constraints, then those make the problem even harder because the rounded solution can easily violate the constraint. So it's really useful to actually be able to solve the problem directly. Okay, so anyway, we have a method of solving this. It's called RiskSlim, and I'm going to tell you about that later in this talk. And that algorithm is the one that produced the 2 helps 2b score. Okay, so after solving the problem, we go back to 2 helps 2b, and now the patient comes in with their burst aneurysm, the hemorrhage in their brain. They get surgery, monitor the EEG. Then the neurologist looks at the EEG and says, oh, the patient has this, this, and that. That's a 2 helps 2b score of 3. I am thus going to place the patient on continuous EEG for at least 72 hours and start them on preventative medications for seizures. Now, so far, 2 helps 2b has been validated on an independent multi-center cohort. This work was done by neurologists. I wasn't involved in it at all. And what they showed was that if you plot the true probability of seizure versus the predicted probability of seizure, we're getting results that are sort of right on that line, which is good. So in other words, the original 2 helps 2b score was created from like the blue, that's what created the blue dots here. There was the original data set. And then in the validation study, they produced the green dots, and what you can see is they're all right on top of each other, which is exactly where we want to be. So it means it generalizes across hospitals. Now, 2 helps 2b has been implemented in several different hospitals. As I mentioned, it's publicly available, so any hospital can use it. And in the validation study, it resulted in a substantial reduction in the duration of EEG monitoring per patient, which allowed the doctors to monitor a huge amount more patients than they were monitoring before. In fact, 2.82 times more patients. And so this, according to the doctors, really allows them to reduce brain damage and save lives. Okay, so I want to talk about the machine learning algorithm that produced 2 helps 2b, which is called RiskSlim. And it involves solving this very difficult mixed integer nonlinear program. But before I do that, I need to tell you about cutting planes, because RiskSlim is a cutting plane algorithm, but traditional cutting planes do not solve this problem. And I need to explain why before telling you how RiskSlim works. Okay, so let me tell you about traditional cutting planes, okay? So let's say that we're trying to minimize the logistic loss, which we know happens to be non-negative and convex, okay? So let's say it looks like this. So here's my logistic loss, okay? Now the way the cutting planes work is we start somewhere. I just chose that point randomly. And then I have to calculate the function and the gradient. I have to create a sorry, plug in here to create a surrogate right here. Okay, so calculate the function and the gradient, and I get a surrogate function there. And this blue thing is supposed to approximate this purple thing right here. Okay. Okay, so now I'm supposed to minimize the surrogate, but the problem is that I know the logistic loss is non-negative. So, okay, so next I'm just going to go over here because I know that, you know, the function value is not negative. So I'll go here. Okay. So again, calculate the objective and the gradient, and then get my line over here. Okay, now I'm supposed to minimize the surrogate. And again, I'm going to choose that point. Go. Okay, again. Calculate the objective and the gradient at a cut. And then eventually, the algorithm will realize that it's found a solution. And when this happens, the algorithm, like when these two functions are equal to each other, the algorithm knows that it's found a minimum of the objective because the minimum of the surrogate equals the minimum of the objective, okay? So that's how it's supposed to work, but something goes wrong when creating models with integer coefficients. So let me show you where that happens. So let's say that you're here in the computation. So you iteratively constructed this surrogate made out of these cuts. Now, when you minimize it, you end up over here. And you can see that minimizing the surrogate involves solving a linear program because all of these are lines, okay? But the solution needs to be at an integer. And so the solution you want could be right over here. And why is that? Because the coefficients, the feasible region are only integers, okay? It's the integer lattice. And this means that you need to solve a mixed integer program at every iteration and not a linear program, because you have to find the point on the lattice that minimizes the objective. And you need to solve the MIP to optimality at each iteration, because otherwise you have no idea whether you've actually solved the problem, okay? So, and still at every iteration you're adding a cut. And so as you add more and more cuts, the mixed integer program that you have to solve at every iteration grows bigger and bigger and bigger and more infeasible by the second, and that's bad. Okay, so no matter how big or small the data set is, after you add 200 cuts, the problem becomes too difficult and the solver totally stalls. So here's an example of that where, after about 70 iterations, you added 70 cuts and the mixed integer programming solver just can't solve it. And after about 10,000 seconds on that iteration, we basically just had to turn it off. Okay, so we have this serious problem with stalling in traditional cutting planes. And the optimality gap, which is supposed to go from 100% down to 0, it just stayed at 100% the whole time. It never went below that. So this is bad. So we designed a new cutting plane method that does not stall. And that is the lattice cutting plane algorithm that's used in RiskSlim. Okay. So with this new algorithm, at every iteration, instead of solving the mixed integer program from the surrogate, it solves the linear program, which is much easier to solve. Okay, so it gives you this solution. Yeah, but we know that that solution's not feasible. So what do we do with it? And the answer is, well, okay, if the LP solver found a point that happens to lie on an integer solution, then we we serendipitously solve the MIP. Okay, so then we can add a cut. Great. So that's one possible thing that could happen. Okay, we could accidentally land on an integer. All right. But if it doesn't land on an integer, well, we know that there are no feasible solutions in here because none of these are integers. And so we're just going to block off this whole area and just tell the solver, you actually can't pick anything in this whole area, okay? And so what this does is it creates two subproblems, one over here and one over here. And we solve those problems separately. We iterate separately in each of the two pieces. So then we solve the linear program in each of the two pieces separately, okay? So here I solved it and I happened to get integer points. And so I can now add cuts, and I can keep going like this by either creating cuts or subdividing the problem into two pieces at every iteration, okay? So it just does this over and over and over again until it gets to an optimal solution. Now this seems to completely solve the problem, because even after 10,000 iterations, we're still taking less than 100 seconds to solve the linear program. And so it just completely doesn't stall. And then luckily the optimality gap goes kind of gracefully down towards 0. And we're all happy because we get the solution to the problem. Okay, so there's no stalling for the lattice cutting plane algorithm. Okay, so let me just recap that in case you missed it. Okay, so if you have the logistic loss here, we want to minimize it over the integer lattice. And we would normally use regular cutting planes, which would give us a solution here. And we're happy because it only involves solving a linear program. But we're now actually not happy because that is not at an integer coefficient, so we're sad about that. So what we do in order to solve the problem is we block off this whole area here and create two totally separate problems to handle those two separate constraints. So you have one subproblem that says, make this coefficient less than 5. And you have another subproblem that says, make this coefficient greater than 6. And then you solve those two problems separately, and they're both linear programs. So if the subproblem leads to a feasible integer solution, you can add a cutting plane. And if it doesn't, you split it into two subproblems, which both of them you solve with linear programs again, and you never go back to mixed integer programs. Okay, and then if you happen to have the minimum of the cutting plane solution equal the objective, then you're done, you solved it. And it will provably converge to the optimal solution. Now, currently, LCPA is the only method that generates solutions within a reasonable time. If you tried to take the problem and throw it into a generic mathematical programming solver, like a MinLP solver, it could take until the end of the universe. And standard cutting planes, as you know, don't work because they require solving larger and larger mixed integer programs, which, as you know, is impractical. Can't do that. Okay, so after we had the RISC-SLIM algorithm developed, and we also had a sister algorithm for it called SLIM, we realized that we can use it for lots of different problems, right? Seizure prediction is only one possible application for it. So we actually used it for a lot of different important medical problems. For instance, we used it for ADHD screening in adults. We used it for sleep apnea screening, and also the clock drawing test. The clock drawing test is interesting. This is where the patient, you're detecting for cognitive decline like Alzheimer's and dementia. And the patient has a digital pen, and they're instructed to draw two clocks as part of the exam. They're asked to draw a clock and to copy a clock. And then depending on what the patient draws, we can extract very subtle signals or sometimes blatant signals from what the patient is creating. So for instance, if the patient is putting little hooklets on the end of their numbers, that gives us information that they had foresight of where they were going to write down the next number. And so that's an indication of better memory, okay? Anyway, we also used it for recidivism prediction, where the goal was to predict arrest in the future for a crime. And this paper got into the center of a battle as to whether black box models are more accurate in criminal justice applications. So stay tuned for that. Now, the question everyone keeps asking me is whether interpretable models are really as accurate as black box models. And now the way that we answer questions like this in machine learning is by comparing, is to compare algorithms by looking at benchmark data sets, okay? So I'm gonna grab a data set, which is the data set from the Explainable Machine Learning Challenge. This is a great benchmark data set, okay? So the designers of this challenge gave us this data set and they said, create a black box and explain it. Because they did not think that there could be an interpretable model of the same level of accuracy as a black box. So they gave us this data set. It was a nice big data set, 10,000 loan applications, 20 some features that have all different information about a person's credit history. And we thought, okay, let's see what happens with this data set. So we ran a whole bunch of different machine learning methods on the data. The baselines we got were 73% accuracy, which came from, boosted decision trees. That's the best we got. And then the best area under the RC curve was 0.8. Okay, so these are the evaluation metrics we aim to match, right, with our interpretable models. Now, the team that came in first in this challenge was IBM, and their model was quite small. It had only 6 questions. Okay. However, they broke the golden rule of interpretable machine learning, which is that they lost performance. So they lost a couple of points in accuracy, and they also lost substantial AUC, because AUC is only between 0.5 and 1. So to go from 0.8 to 0.62 is quite bad. Okay. Now, our entry, which won the Fico Recognition Prize, didn't have this issue. It had accuracy was just on par with the black boxes, AUC was also on par with the black boxes. We didn't sacrifice any performance to get an interpretable model. And the way we constructed our model was through 10 little itty bitty subscales. They were like very similar to the scoring systems I've been talking about all this time, okay? So we had 10 subscales. I'm showing you just like a snapshot of our visualization tool for this model. And there were these 10 subscales, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the subscales involve just 1 to 4 features. And I'm going to zoom in on the biggest subscale here, which is the delinquency subscale, which involved these 4 features about how delinquent you were with repaying your loan. And this is an example of a person who's getting their delinquency score evaluated. And this person was delinquent fairly often. In fact, they were delinquent between 59 and 84% of the time. And so they get a point for that. And then their most recent delinquency is between 0 and 8. So within the last 8 months, they were delinquent on something. And so they get more points for that. And then, there's some other stuff here that gets added up together to produce an overall score. And then there's a bias term, we add that to it. And then that translates into a risk through this link function over here. And this person has a 79.8% chance of defaulting on a loan. So it was very simple. It was just like a bunch of scoring systems, right? So what I'm trying to tell you is that even on challenging benchmark data sets, we're not finding that you're going to lose performance to be interpretable, right? We're getting that the interpretable model's accuracy is the same as the black box accuracy. Okay, so now I want to go back to the topic of criminal recidivism in the COMPAS score. And as I said, this paper got into the center of a battle as to whether black box models are more accurate in criminal justice applications, because we claimed that we could construct interpretable models that were the same level of accuracy as the black box. Now, something you need to know here is that explaining a black box is not the same thing at all as creating an interpretable model, right? These are totally different. If you create a model to approximate a black box, then it's an approximation, it's not an explanation, okay? Because the black box and the explanation could involve totally different variables, okay? So you could have these 2 models, like this one approximates the more complicated one. So let's say this one's the black box and this is the approximation. They could depend on completely different variables depending on how variables are correlated. And so it's entirely possible that the black box, that the approximation could depend on age, number of prior crimes, and the race of the person, when the black box actually only depends on age and number of priors, right? That could happen because you're making an approximation, right? And you might get into the situation where someone thinks that because the approximation depends on race, other than through age and priors, that the black box also depends on race. And you could say, well, this would never happen, right? This is silly. Nobody would do this. But it actually might happen. And it actually did happen. And it happened with COMPAS. And in particular, it happened in this very famous ProPublica article that everyone talks about. So this is exactly the mistake they made. They took COMPAS, they approximated it with a linear model. The model depended on race, and then they declared that COMPAS must thus depend on race in a way that is not through age, its correlation with age and number of priors. So let's go through what they did, okay? So what ProPublica did was they showed that the false positive rates and false negative rates of COMPAS varied by race. And they said, they actually wrote in their article that maybe this might not be a good comparison because we should really include age and number of priors and re-examine, because the correlation of race with age and race with number of priors, that's all due to systemic racism in society, right? That doesn't necessarily mean that COMPAS depends on race in a way that's not through those factors. Okay, so after including age and number of priors, ProPublica still found a linear approximation to compass with a low p-value for the race covariate. So that they're taking that as compass depends on race. So they concluded that compass depends on race, okay? Now the problem, I think, happened where they approximated compass with a linear model, because I don't think compass is linear. And so I think their conclusion doesn't really follow, okay? So let me show you why their assumption was particularly bad. So I'm going to grab that data from Florida that was used in the ProPublica piece, okay? So the compass data, and I'm going to plot it. I'm just going to plot it. So this is a scatter plot of compass score versus age. So each dot here is a person, and this is their compass score, and this is their age, okay? And I hope you can see this, but there is a sharp curve over here. I mean, like somebody who's 60 years old is getting compass scores that a person at 20 cannot get, okay? It's not, there's this big gap over here. There's no scores in here. And there's a few that go below this curve, like this is a fairly sharp cutoff. There's a few people below that. And, you know, maybe there are a few outliers, maybe some typos in the database or something, but overall, not pointing to a linear function of age. And, you know, you could try to create a linear function of age, but I just don't see it. I just don't see it happening. And it looks like compass depends very heavily on age, particularly for younger ages. And so if they messed up the dependence on age, that could definitely mess up their analysis. So we were wondering, okay, we created this sort of, you know, we created this piecewise linear approximation to this lower curve here. And we thought, you know, maybe that is how compass depends on age. So we said, okay, let's try subtracting that out. Okay, we'll subtract that out, and we'll see if compass still appears to depend on race. Okay, so we said, fine, we'll take out that curve, and then say, does the remainder depend on race, right? And it really didn't seem to. In fact, we ran machine learning methods with and without race to see if they need race to predict compass well, and they perform very similarly, which is in agreement with our earlier paper that said that race does not contribute anything to recidivism predictions other than through its correlations with other factors. So yeah, race doesn't boost performance. And ProPublica's analysis, pretty shaky. So then if race doesn't actually appear in compass other than through its correlation with age and criminal history, then I was wondering, like, okay, how did they find these pairs of people? Because these examples were key evidence on how compass depends on race, right? So they had these pairs of people. It was a white person paired with a black person, and then in each case, the white person had a much lower criminal history, and the white person had a much higher criminal history and a lower compass score than the black person. Like she has like 4 juvenile misdemeanors and like is considered high risk, okay? Whereas this guy, 2 attempted robberies, he's low risk. How could that possibly happen, okay? And they found a bunch of examples like that. And the thing is, if you look at these 2 people, the black person is much younger than the white person. So if compass depends heavily on age, that could totally explain how this happened. Like Vernon Prater, he's old, so he doesn't get age points, right? And I'm not saying I agree with this, but if they had compared 2 people with the same age, then it would be much more convincing that compass depends on race in addition to the strong dependence on age. So ProPublica's claim, you know, not really holding up with respect to race. Compass might not actually depend on race other than through correlations. But I think there's a much worse problem with compass that ProPublica completely missed, which is that humans are not very good at inputting data reliably, which is what caused the issue with Glenn Rodriguez. So, you know, if you have even a 1% error rate on entering information, then there's at least a 75% chance of at least one typo on a survey, which is a huge disadvantage to complicated or proprietary models. And like I said, this is exactly what happened with Glenn Rodriguez. So we were looking at the Florida data to try to figure out how often these typos might happen. And we found some strange inconsistencies in the data. And Here, for example, is a list of people who have a COMPAS violent decile score of 1. This is the lowest possible COMPAS decile score. The maximum is 10. And so these people have the lowest possible score. But if you look at their criminal history, it's like, really? You know, like this person has a history including robbery with a deadly weapon, aggravated battery with a deadly weapon, driving under the influence, carrying a concealed firearm. And that person gets a COMPAS score of 1? And I just can't explain this other than data errors or some kind of error in the calculation of these scores, like some issue. This is just the tip of the iceberg. These are people with COMPAS scores of 2, 3, and 4. So again, very low risk. And look at this, this is the number of prior charges and the number of prior arrests. And it's like, whoa, like how is it possible that these people can have COMPAS scores that are so low? We even found what we think are typos in COMPAS documentation. Like COMPAS claims that they have a linear model with respect to age, whereas we think that it's probably nonlinear. So anyway, we published this article attacking both ProPublica for explaining a black box model wrong, and COMPAS for being a black box where typos cause decisions. And the editor that handled our paper, the famous Zheli Meng at the Harvard Data Science Review, solicited a whole bunch of commentaries on our paper. And they were from famous criminologists and famous sociologists and lawyers. Anyway, but one of the criticisms or one of the commentaries is from the people who created COMPAS. And they wrote an absolutely scathing article saying that COMPAS is interpretable, which is pretty funny because if that were true, then it would have saved me and ProPublica a lot of trouble. But in the mountain of criticism there, they admitted a couple of things that were super interesting. So they wrote, that the authors, which is us, that we have taken a clearly informal description of the COMPAS violence score in the practitioner's guide. And it was not, the guide was written for practitioners and it wasn't intended to be a technical document. Discussions of appropriate variable transformations are beyond its scope, which is really funny because they're saying it's an informal description, but it's an equation. I don't know how much more formal you can get. It's an equation. And they're saying, discussion of appropriate variable transformations are beyond its scope, which is like, wait, maybe we're right. Maybe there is a typo in the practitioner's guide. It's typos everywhere. And they also wrote at the end of their article that they're pursuing copyrights for their scores. And, maybe it's a sort of subtle admission of guilt there, maybe we actually made a difference. All right, so just to summarize, scoring systems are good when you optimize them. Typos are bad, and those happen more often with complicated or black box models. And evidence suggests that we don't need such models in the justice system. All right, so just to wrap up here, I wanted to tell you about the problems we're working on in my lab now. And so you've heard all about scoring systems, and we've got a bunch of other cool stuff going on. We've got work on optimal sparse decision trees, which you've seen a little bit of that because the Corals work is from that branch of my lab's work. And so we've been trying to design really tiny little optimized sparse decision trees. We've also been working on interpretable neural networks for computer vision, and specifically with applications to mammography, computer-aided mammography. And we've also been working on neural disentanglement. I also have part of my lab working on dimension reduction for data visualization, where we're trying to take high dimensional data, map it onto 2 dimensions, and still preserve the interesting high dimensional structure in the data. I'm also one of the co-PIs of the Almost Matching Exactly lab, the AME lab, which works on matching for causal inference, where you're trying to find, if you have a data set and you're trying to find the causal effect of like some drug, and what you can do is try to match treatment units, like people who've had the drug with people who haven't had the drug that are very similar to each other, and try to use that to approximate what would happen in a randomized controlled trial to figure out if you can estimate the effect of the drug. And then the last projects are on understanding the set of good models and the importance of variables. Because you don't always just want like the best single good model. You might want to have the domain expert look at lots of different models and be able to select one. All right, thank you very much.
Great. So thank you, Professor Rudin, for this very exciting, very interesting talk. I think it is amazing to see how can we use machine learning and optimization to actually fix some of our issues with our socio-technical system. So this is great. So now we can have time for questions. So it seems that Subramanian has a question, so I'll just give you access to
yeah, I can see here. So
yeah.
What are the limitations of interpretable machine learning models? Okay, so one reason people don't want to construct interpretable machine learning models is that the optimization problems are harder because you have to put in the constraints to make the model interpretable. And as soon as you add the constraints, then the optimization problem becomes really hard, like I showed you with scoring systems. And then also, once you realize that the model, once you start putting interpretability into these models, you look at them and you're like, this is not behaving the way that I think it should. And so because of that, then you have to go fix it. And so there's this big loop and this very big time-consuming loop that when you realize all the things that are wrong with your model, you want to go fix it. And it takes a longer time. So it is just harder to create interpretable models. And then also another limitation is that when you're working on something like computer vision or sound waves or something, it's not always clear what interpretability means. And so you have to create a definition of interpretability that matches the domain. And that's also not the easiest thing in the world sometimes.
Great. Yeah, so you can type your questions or raise your hand and I'll give you access. Yeah, so yeah.
I have a review paper that we just wrote on interpretable machine learning, and I'm just going to put it, since there are a lot of students in the audience, I'm going to just put that, see here. I'm going to put our review paper here. Grab a link. Okay.
Yeah. So Subramanian, do you have another question, or is your hand still raised from the previous one? Sorry, I cannot tell.
There we go. Are Fico scores an interpretable machine learning model? No, they are not, because do you know how to calculate a Fico score? Because I don't, and it's proprietary. And in fact, all of the major models that the finance companies create, they're all proprietary. So because they're proprietary, they are not interpretable by my definition. They're actually black box models. What am I going to say about that? Sometimes Fico will give you an explanation as to why your credit score went up or down. And some of those explanations are a riot. When I paid off my loan for my house, my credit score went down because, they said that I didn't have as many, I wasn't paying money regularly to more, people who lent me money. And so my credit score went down, which is how is that even possible? Okay, here's some more questions.
Yes, I think Arley has a question there, and Guha.
Oh wait, there's a company called Upstart that's a replacement for Fico. I didn't know about it. Thank you for telling me. I'll just write it down. Okay. Are interpretable models necessarily then interpretable approximations for black box models? Well, I showed you a case where an interpretable explanation for a black box model led ProPublica to write an article saying that Compass depended on race when it actually may not. So yeah, interpretable models are necessarily better. They avoid a lot of the problems that go with explanations of black boxes. In fact, I wrote a paper a couple years ago that told everybody to stop explaining black box models and use interpretable models instead. So let me grab the link for that and you can check that out. Copy link. link. There we go. Okay, cool. Okay, how do you reduce dimensionality through SVD? No, so for the scoring systems, the way we reduced dimensionality was through an L0 norm. If you try to use SVD, that will actually ruin interpretability because it will create a linear combination of all of your features to be the new axes for your reduced space, and you will have made your problem completely a giant mess. So yeah, SVD or PCA completely will mess up your interpretability in that case. Okay, have you found any applications where scoring models have an implicit bias that doesn't work well compared to other machine learning models? I mean, certainly, that's a good question. So for tabular data, we haven't found that. Like even for the Fico challenge data set, we've done really well with these tiny little, like I showed you, the little tiny little scoring systems that you put 10 of them together and then you create a scoring system from those 10. It was like 11 logistic regression models. And there were some nonlinear transformations in between, but it was still, these tiny little scoring models. So, not everything is going to be linear, but you can usually find a way to break down the problem to get something that's interpretable and still very accurate. Oh, sorry, I'm confused here with this last question.
Yeah, Arle, maybe you can just ask your question. I just gave you permission to talk.
Yes. Hello, Cynthia.
Mm-hmm.
Can you hear me?
Yeah.
Sorry. I just because you talked about the explanation, and then I asked about approximation. So I just got. I don't know if you mean that these two things are the same thing. Like one thing is explaining your model, the other thing is approximating, right? So I could give you an interpretable approximation of my black box model. So that's what I was asking about.
Oh, okay. Well, I think it's fine if you want to create an approximation of another model. Just don't call it an explanation. Don't say that you're explaining the other model when you're just approximating it. You might be able to use the approximation for prediction. That might be perfectly good, but it's not telling you what the black box is doing.
Okay, it makes sense. Thanks.
Yeah.
Thanks.
Sure. And the medical scoring examples are all covariates binary. I would think that for continuous covariates, the scale of these input covariates may be more important to calibrate. So exactly for that reason, we actually transform everything to binary variables. So if we have a continuous feature, we'll transform it into a whole bunch of binary variables. And then that allows us to create essentially additive models because they're like step functions with respect to the original dummy variables. So we always transform everything to be binary so that everything's all on the same scale for exactly the reason you mentioned. And then the last question I love, thank you for asking that. Does an interpretable machine learning model exist in every situation where a black box machine learning model exists? That's a question I've been spending my entire career trying to figure out the answer to. So I started working with, I started working on power grid reliability, working with the power company of New York. And there, the black box was making the problem worse because we couldn't troubleshoot the model. And so we started using like scoring systems, and it was just so much easier to communicate with the power engineers and stuff. So that actually made it more accurate. And then I spent my whole career just trying to go between different problems and trying to find a case where I needed to sacrifice accuracy. But even in computer vision, we haven't had to sacrifice accuracy. And now I work in material science, and there we're not even using neural networks for the material science problems, which is kind of unheard of in material domains. So I don't know the answer, but I suspect the answer is yeah. So far so good.
Great. I think this is a good set of quite interesting questions. Maybe I can ask one, which is from the point of view of optimization people. So we are obsessed with finding the minimal point, right? And it seems like if you want interpretability, you need to sacrifice a little bit of optimality by constraining your solution, let's say, to a set of integers type of things. Is this a way to sell? Like we don't really need like more complex and larger models, but if we strictly small things we can do better. Maybe we will not get the smallest possible loss, but maybe something that we can actually understand what's going on.
Yeah, that's true. I mean, in many cases, you might be willing to sacrifice performance for interpretability. And maybe the reason that the black box is doing so well is because it's depending on factors that it's not allowed to use. You know, like confounding variables. And like, yeah, okay, my performance went down, but at least I know my model is going to generalize now because it doesn't depend on the type of X-ray equipment that we're using. So yeah, that's definitely a good point. So I have this theory as to why interpretable models exist so often, which is that I think that there's just a lot of good models, and because there's so many good models, like if you have say a sphere of good models, then by approximation theory, you should be able to find an interpretable model in there somewhere, because as long as the set of interpretable models kind of covers the space, then within every ball there should be at least one interpretable model. And so I've been trying to formalize this theory, and we have a paper online that talks about that. I think it's a reasonable explanation for why interpretable models exist so often that are accurate.
Yeah, so we're a little bit of over time now, so we don't want to take more more time out of your time. But if you feel like answering this last question is up to you, or we can close for now. Yeah,
I can answer it. It's fine. Okay. Could you comment on the applicability of integer values? So integer values, you don't need them for every problem, of course. Integer values are useful for when you have like a doctor in a room with a patient, you know, where you need to be able to calculate scores really quickly and understand counterfactuals really quickly, and just be able to compute all possible situations in your head. And you know, I mean, like I said, scoring systems have been used for 100 years. People have designed those models of that form for 100 years. So they have a lot of historical, you know, there's like a lot of precedent for them. And I find them quite useful myself. I just think they're so beautiful and cool that you can have a tiny little model like that. And even biostatisticians spend a lot of time like rounding coefficients and playing with logistic regression coefficients to get them to be integer. And so we were like, you know what, we can do this, we got this. So that's why.
Thank you. Yes, so okay, so with this, maybe we can conclude now today's data science seminar. I think it was very interesting, a lot of audience participation, that's great. And again, thank you, Professor Rudin, for joining us today. And yeah, thank you all, everyone, for joining. And I hope you have a good end of the week and exams week as well. So yeah, I'll finish now with this. Okay. Thank you. Bye.
Thank you. Bye.